At its peak in the 1st and 2nd century AD, the Roman Empire had an estimated population of 60 to 75 million people, a level unmatched in Europe for over 1,500 years. This period, known as the Pax Romana, was a time of stability and prosperity. However, it also coincided with the emperor's peak wood consumption, which largely contributed to the collapse of the Western Roman Empire in 476 AD. In this video, we'll be exploring how the situation today for the modern economy is not very much different than the situation the Romans faced 2,000 years ago. We'll also be talking about how we can avoid their fate by adopting existing technologies, which will spawn a new era in human civilization where almost anything will be possible. From greening the Sahara Desert to interconnecting the world with newer and better infrastructure to reversing all manner of environmental problems because we have the energy to do it. So let's jump in, but as always, please don't forget to like and subscribe to the channel so that important information like this can get out to a wider audience. Thank you. Modern society was born 150 years ago during the Industrial Revolution when coal began providing sufficient energy for steel manufacturing and steam-based locomotion. Today we are high energy using civilization globally, which relies heavily on commodity extraction, food production, and manufacturing, all of which depend on a foundational energy source that is both widely abundant and cheap. To illustrate the point, let's imagine an island whose economy is centered around the mining of precious stones. Initially, the island is equipped with fossil fuels and machines, and is therefore able to extract the stones efficiently and at low cost because it can dedicate a large share of its collective effort to extracting the precious stones rather than mining for energy to fuel the equipment. And with all this excess energy, perhaps it even has extra for investing into schools, hospitals, and other kinds of amenities for society. But now imagine the island's energy return on investment, or EROEI, gets cut in half. In this case, they'll have to dedicate more of their labor to extracting energy and less towards extracting the precious stones. This means fewer stones at a higher price and probably fewer amenities like schools and hospitals. Finally, imagine the island has lost its energy source altogether. Therefore, with only human labor to rely on for digging up stones, perhaps they'll quit mining and shift their efforts to fishing or some other endeavor that is less profitable but still economically feasible given the limited energy source at their disposal. Now, with this example out of the way, I'd like to argue that the world today is transitioning from an Island 1 scenario to an Island 2 scenario. In fact, according to Peak Oil and the Low Carbon Energy Transition, a Net Energy Perspective by Luis Deloni et al. 2021, we already reached a peak in net oil production around 2019. And after 2030, net oil production is set to fall swiftly downwards. This means that, like Island 2, energy extraction will be increasingly draining on our productive capacity as time goes on. In other words, our energy return on energy investment, or EROEI, will begin to fall rapidly after 2030, according to this report. Making matters worse, in 2035, even the gross production of fossil fuels will peak. Once this happens, the fall off the energy cliff will simply accelerate, making our civilization look more like Island 3 as the years roll on. And further research confirms these estimates, as can be seen from these two graphs. So to conclude, we need a viable alternative and quickly to divert the energy cliff and avoid the economically devastating impacts on commodity-driven inflation, loss of industry, and possibly even demographic decline. Taking a step back, let's appreciate the massive role that fossil fuels have played in increasing global GDP and population since the 1800s. For example, since the early 1800s, the total world population exploded from 1 billion people to 1.63 billion people in the 1900s, then to 3 billion people by 1960, then to 6.1 billion by 2000, and roughly 8 billion today. Meanwhile, the global GDP ballooned from 1.45 trillion equivalent in the early 1800s, then to 3.4 trillion equivalent in the 1900s, to 13.25 trillion in 1960, and a staggering 113.6 trillion today. And the correlation between GDP and per capita energy consumption could not be more clear, as is shown from this chart. However, as I've mentioned, the global energy landscape is facing a critical turning point. To put some numbers on this, in the 1930s, the energy return on energy investment for US oil was near 100 to 1, which means that it took 1 barrel of oil to extract 100. In the 1970s, that number fell to roughly 30 to 1, and today the EROEI for oil is roughly between 4 and 30, depending on the specific circumstance of the extraction. And this is a scary notion given the projected increase in energy demand, according to this ExxonMobil report, from now to 2050 to beyond. And with the world completely dependent on cheap and abundant energy from fossil fuels, it's very hard to see how this energy demand is going to be satisfied. So, what's the solution to the energy cliff? Natural gas, maybe? While it's true that natural gas is both cleaner than other fossil fuels and has a higher EROEI than oil, shale rig counts are starting to wane, at least in the US, meaning that there will be less natural gas online in the near future. In fact, according to a tweet sent out by energy expert Steven St. Augustino, the annual energy decline rate of shale gas production is 32%, which means that ever more shale gas rigs must be put online for production to stay flat or grow. However, for the Haynesville gas field, which provided 50% of the total shale gas production growth in the past 3 years, the gas rotary drill count is falling precipitously. Does this mean that there's not enough natural gas production online to fuel the next wave of economic growth? The honest answer is I don't know, but the trends in the Haynesville gas field are not looking very promising. So, is the solution renewables? Well, frankly, these solutions are at best laughable and at worst extremely dangerous to consider. First of all, solar PV and biofuels both have an energy return on investment of below 5, which is below the minimum requirement to sustain modern civilization. And when comparing these to fossil fuels, which have an energy return on investment of at least 30, it really begs the question as to why we're even considering this as a feasible alternative, especially when policymakers know full well that these alternatives wouldn't even exist if it wasn't for fossil fuels to manufacture, ship, mine, and do all the other things that are required to produce them. In other words, the massive success of fossil fuels provided the luxury environment for these environmentalists to push for these green energy technologies which don't actually work by themselves. And without fossil fuels, renewable technologies would completely vanish. Furthermore, if we snapped our fingers and we were able to transition the entire world economy off of fossil fuels and to solar, wind, and biofuels, not only would we not have enough energy density to run the modern economy, but we would also have a devastating impact on the environment because of all the amount of land that's required to basically put these solar panels and wind farms up and grow the corn and wheat that are necessary to produce biofuels. So the idea that these are green, sustainable technologies that can stand on their own 2 feet is a complete fallacy. And again, the break-even number for fueling a modern society is around 7. Below 7, everyone would be deploying their efforts just to stay alive. Above 7, the society can develop a complex economy, division of labor, industry, transportation, construction, and all that good stuff depending on how high the energy return on energy investment is. And while I've really hammered on renewable technologies because they have an EROEI below 7, I do want to point out that wind in some applications does have an energy return on energy investment above 7, which actually makes it a feasible, possible solution in the overall energy complex. However, given that it's intermittent and unreliable, it cannot be the only solution. And in fact, with a optimistic energy return on energy investment of 16, the truth is that there are just better solutions out there. In fact, as that Forbes article puts it, if we are to enter a cleaner energy future and to continue to lift people out of poverty around the world, every country's energy mix has to have the highest EROEI as possible, or it will not be sustainable or acceptable to humanity as a whole. So with this clearly and intuitively being the case, the best long-term solution is nuclear power because it has an energy return of energy investment of 75, all with a carbon intensity of near 0. But not only does it have the highest energy return on energy investment according to this article and many other sources, but when pairing some extremely high energy dense nuclear technologies with very low cost fuel, the potential energy return on energy investment for nuclear power can even exceed 100,000 or even in the millions according to some. So just imagine the kind of world that we could have if the energy return on energy investment for our primary energy source was not in the 30 to 40 to 50 range, but in the 100 to 1,000 range. But not only that, nuclear energy has the highest energy density of all other energy sources. In fact, according to the book, The Power to Save the World, one uranium fuel pellet, which is about the size of a drill bit, contains the same amount of energy as 149 gallons of oil, 157 gallons of regular gasoline, 17,000 cubic feet of natural gas, or 1,780 pounds of coal. Pretty remarkable. More interestingly, the amount of land that will be required to transition the entire global electricity production onto nuclear power is extremely tiny. According to my back of the napkin calculations, if we assume an energy density of about 1 square mile per gigawatt at 70% efficiency and a total global electricity consumption of 25,500 terawatt hours, nuclear power plants would only require 36,000 square miles of land, which is about the size of Indiana. By comparison, if we wanted to replace the world's electricity consumption with solar panels, and we assumed a solar efficiency of 20%, peak sun hours of 5 hours per day, and a solar PV energy density of roughly 6 acres per megawatt, we'd require 2.3 million square miles, an area roughly the size of Ukraine. So why haven't we already transitioned to nuclear energy? I mean, we've had this technology since the 1950s. Well, if you listen to Malthusian organizations like Greenpeace, the answer is that nuclear power delivers too little to matter, it's dangerous, it's too expensive, it's too slow, and it produces too much toxic waste. All these statements are patently false and deliberately misleading. So let's go through them one by one. The fact of the matter is that nuclear delivers more primary energy than all renewable sources, despite the active and ongoing fight against nuclear, while renewables are subsidized to the nth degree. And in fact, according to worldnuclear.org, combined investment in energy efficiency, renewables and hydrogen and fuel cells is about twice that of nuclear, but with less to show for it in terms of electricity supply. And number two, nowhere in the world is nuclear power subsidized per unit of production like they are with renewables. In some countries, however, nuclear production is taxed because it's so cheap to produce, which further exacerbates the distortion in the energy markets. Additionally, the regulatory hurdles are deliberately designed to prohibit the construction of new nuclear plants. For example, according to the Power to Save the World, the annual exposure to the public permitted by the EPA for nuclear facilities is 15 millirem. By comparison, an abdomen X-ray gives off 60 millirem, and foods like bananas, carrots, potatoes, meats, and more all have high levels of radioactive potassium and radium. In fact, the average nuclear worker receives much less radiation than the average flight attendant. But I don't see anyone whining about radiation when they go on airplanes. Plus, according to the Power to Save the World, there's an abundance of evidence that low levels of radiation are not even harmful. But knowing this full well, the powers that be have still weaponized the public's fear of radiation to kill the industry in its cradle with red tape, high costs, and propaganda. In fact, costs are so artificially high because of these nonsense regulatory hurdles that nuclear power is considered one of the most expensive power generating sources, while solar is considered one of the cheapest, according to Statistica. Now I ask you, how could that possibly make sense if nuclear's energy return on investment is 75, while solar's is 4? The answer is it doesn't make sense. The powers that be are actively fighting against the laws of thermodynamics and robbing civilization of the cleanest, most energy dense, and highest energy return on investment energy source ever discovered, just because they don't want civilization to have cheap and abundant energy. Because think about how much power they would maintain if all their serfs had plenty of energy and abundance to live off of, and all their colonies would be lifted out of poverty. Just think about it. Anyway, the idea that nuclear power cannot deliver enough energy, is too expensive, or is even dangerous are not only misleading, but are outright lies. And to put the icing on the cake, the notion that nuclear power is dangerous is completely laughable. In fact, nuclear has the lowest death rate per unit of electricity production, apparently only seconded to solar, which I find extremely hard to believe considering that thousands of people have to go up on their roof every year to fix and clean their solar panels, and lots of them get hurt. However, full transparency, there are dangerous nuclear energy technologies known as breeder reactors, which basically as a byproduct produce fissile material that can be used for nuclear weapons. And these technologies, by the way, are the primary technologies that have been built and deployed today by the psychotic Anglo-American military-industrial complex because they wanted all these nuclear power plants to just build bombs out of. However, Generation 4 reactor technologies like integral fast reactors, TRISO fuel reactors, and thorium molten salt reactors solve this proliferation problem. Not only do many of them produce 1% of the nuclear waste as conventional reactors, but they can even cannibalize waste products from older reactors as fuel input. So how's that for a toxic waste problem, Greenpeace? So to conclude, a global energy transition must occur quickly in order to sidestep the negative effects of the energy cliff that's rapidly approaching. With little to expect from intermittent and low energy return on investment renewable technologies, the only real possible solution is nuclear power. If we all wise up to this fact and force political change, not only would we sidestep the energy cliff, but also produce a new era of human flourishing that honestly would be awesome to see. And before closing out, please don't forget to like and subscribe to the channel. Throw your thoughts and comments down below. Thank you for sticking with me, and I'll see you on the next one.